In this video, we'll look at some examples of applying some of the things we've learned in the earlier part of this section about analyzing a symmetric laminate. And we're looking at a couple of problems. We're going to actually look at a couple of variations of this particular problem. So we'll say that we have a drive shaft for a cooling tower, and it's got a transmitted torque 75,000 inch-pounds. The nominal diameter is going to be 6 inches, and it's going to be made out of carbon epoxy. Now, to begin with, we know that plus or minus 45 degree laminate, balanced laminate, works well for torsion resistance. And so we're going to try to find the optimum thickness, or the best thickness that meets a design factor of 5. So the compressive stress in the fiber direction we want to keep at less than 30,000 psi. Again, the compressive strength of this material we've rated at 150,000, so we'll just divide that by 5. The in-plane shear is, the strength is 14,000 psi, so again we divide that by 5, and we want to keep that magnitude of the shear stress at less than 2,800 psi. Okay, so remember from last time we looked at when we have a torsion on a tube, we can calculate the stress resultant in xy as such. And that works out to be 1,326 pounds per inch. And so just arbitrarily, we're going to just try using 1/10 of an inch for both the plus 45s and the minus 45s and see what we get. So I'm going to switch over the spreadsheet here and go to the beginning. And so here's our plus and minus 45s. You can see both of these are material code 1, which is carbon epoxy. These are set to 0, so we can ignore everything that's going on over there. And here are the stresses when we put in this value of nxy. I put the equation in there, so that's why it comes out to more decimal places than the 1326 I showed on the PowerPoint. So here are the stresses, and you notice that the plus 45s go into tension and the minus 45s go into compression, and that there's no shear stress, in-plane shear stress in the local coordinate system. So there's the stresses, and since this is a linear problem, that is, if we increase the load, the stresses increase linearly. If we increase or decrease the thickness, the stresses change linearly as well. So all we have to do really is to ratio the minus 45 thickness so that we hit the critical value of minus 30,000 psi, 30,000 psi compression, that is. And if we do that, excuse me, we come up with a thickness of the minus 45s of 42 thousandths of an inch. And again, we want it to be balanced, so we set the plus 45s at the same thickness, and it's a little less than 1/10 of an inch. 85 thousandths of an inch is our total. And again, we saw that one group of the layers went in tension while the other went in compression. So in theory, could you say, well, the plus 45s tended to be not critical, so could we just reduce the thickness by having different thicknesses of plus and minus 45s? You really don't want to do that, because if you did put a twisting moment on there, the shaft would twist in a non-symmetric manner, so it would start to bend as well. Also the shaft, most of the time you're going to design that so that you can twist it in either direction with the same factor of safety. And if you made this shaft by filament winding, which is most likely, then that process always creates a balanced laminate. So having a balanced laminate seems like a good idea here for our design. All right, so let's change it up a little bit. And a lot of times when you have a drive shaft, it's maybe lengthy and under its own weight have some bending associated with it as well. So we're going to look at a bending moment of 80,000 inch-pounds. That's going to be applied in addition to the torque that we just showed. And again, a plus and minus 45 laminate. What's the required thickness? Let me go back to the spreadsheet here and look at variation A. So once again, we've just arbitrarily set the thicknesses to 1/10 of an inch each. And here's what the stresses come out. So you can see the n of x has been applied. We'll get to that in just a moment, as in the negative value. And here are the stresses. So yeah, there's our n of x value. Again, plus or minus m divided by pi r squared. And so we're going to use the negative value because the compression stress is critical. And here are the stresses then that we just showed you off the spreadsheet. And in this case, notice, this is less than 30,000, so theoretically we could make it thinner and bump this up to 30,000, but this is way over. Both of these are way over our 2,800 psi maximum in-plane shear. And so we have to ratio, this case, the thickness upward, and we need about a 1/4 inch of both the plus and the minus 45. So our total thickness is over a 1/2 inch. So not very good. And again, that's because the plus and minus 45s are really not a very good design for the axial loading. They're really good for the torque, but not so good axially. So let's do a little variation. Say if instead of having to use 45 degrees, what if we make that angle theta? We can vary that and still look at the same torque and the bending moment. We still want the laminate to be balanced, and what's the required thickness of that plus and minus theta laminate, and what is the value of theta as well. Now again, the laminate's got to be balanced, so in the spreadsheet we're going to set the angle of layer 2 equal to the negative of the angle of layer 1, and the thickness of layer 2 equal to the thickness of layer 1. But now we have more than one independent variable, so we can't just do the simple ratioing like we did earlier. So we're going to use Excel Solver. And our solver model is this. We want to minimize the total thickness with these constraints. Sigma 1, we want it to be greater than minus 30,000 psi. In other words, the compressive stress less than a magnitude of 30,000 psi. And we want the magnitude of the shear stress in both layers to be less than 2,800 psi. So we have to do that by saying tau 12 is less than 2,800 and that tau 12 is greater than minus 2,800. All right, so here we go with variation B. Now again, in this case we're going to use solver. You can see we're set up here that we want to minimize the thickness by changing these two cells, this thickness and this angle. Now we already have this one being equal to that one just within the cell, and we also have this angle being equal to the negative of that. And so here are our constraints. You can see how they're added one at a time here. Well, actually, let me just do a change instead. You can see we just have to highlight all of the values. Well, in this case we just have 2 layers, but the sigma 1 value of both layers have to be greater than or equal to minus 30,000. And similarly, the shear stresses less than 2,800, shear stresses greater than minus 2,800, and let's hit solve. And so what we find is the optimum angle is about 22.4 degrees, and we end up with a thickness of about 2/10 of an inch. So it was a 1/2 inch if we used plus or minus 45s. When we optimized the angle, came out a good bit lower. All right, so instead of just using the plus or minus angles, what if we say that we know that plus or minus 45 is really good for torsion, and we know that 0 degree is good for axial loading? Let's find the laminate that works best here, least thickness possible with 0 and plus or minus 45s. So once again, we're going to use solver, and once again we'll have 2 independent variables. In this case, the thickness of the plus 45, the thickness of the minus 45 will match that, and thickness of the zeros. All right, so here's our version C. So arbitrarily, I've set 1/10 of an inch here and 1/10 of an inch here. Again, this value is going to be equal to the value of the minus 45, and you can also see that this angle is just, well, we can just make it minus 45 because we're not going to change that. The things we're going to change are going to be this cell and this cell, these 2 thicknesses. And again, the 4th layer is set at 0, so we can ignore everything from there. And again, our solver model has pretty much the same constraints, although this time, if we look at one of these, oops, sorry, let's pick this one and hit change. You can see we've just applied it to all three of the layers and said that sigma 1 has to be greater than or equal to negative 30,000 psi. And with that, we can go to solve. And we find that, yeah, we get a better design than we had with just the plus and minus theta, and certainly better than the plus and minus 45 degrees. So here's our thicknesses of the plus and minus 45, and then we add about 80 thousandths of carbon epoxy to that. And so there's again our total thickness. So again, this tends to be an efficient design because of the fact we have the zeros in there for the bending, the axial load, and the plus or minus 45s in there for torque. So what we did this when we looked at these normal and shear stresses independently, what we're really doing is applying a maximum stress failure criterion. And when we get into the next section, we're going to look at an interactive failure criterion, much like the von Mises is an interactive criteria for ductile isotropic materials. We'll look at one that looks at the failure modes altogether instead of independently like this. But before we get to that, we'll do one more example, one that I've talked about earlier, where we tried to design the carbon epoxy cases for the Space Shuttle solid rocket boosters to replace the steel cases.